Hello, and welcome back to the MCAT grind. This is BioChem number 2 for enzymes. So, if you heard of enzymes before, you know that they're very important in both the MCAT passages and also our human body. Without enzymes, a lot of the progress and the reaction just cannot happen, and hence they're just so important that we will go over it in this chapter specifically. So, with enzymes, they are these molecules, biomolecules, that catalyzes the reaction, which means that when substrates enter the site, it can be like two compounds or any molecules that go in, and if they want to bind together to form a product, this enzyme will help it happen. Think of it this way. Substrates, naturally, you have this green and blue blob. If you let it float around in the bloodstream, eventually they could clump together, right? But that just relies on luck and letting them float around and just coincidentally bind to each other. With this enzyme, however, in the presence, it has a certain part that allows them to, stay to one another and bind to another, right? Think about students. If you and your friend are just wandering on the campus, of course, by chance you bump into each other. However, if there's certain classes you're taking together, then at that classroom, you would meet each other, right? A lot more likely. So think of the classroom itself as the enzyme. Now the product will form a lot easier due to the presence of the enzyme, and there are some categories, or here's a visual representation of what it does. G is the Gibbs free energy, or the energy of the product, or just any compound. As the reactant, it has a certain amount of energy and it wants to bind together to a state so that it lowers into a product state. What that means is, to go from reactant to product, you need to give it some kind of energy, like activation energy, for it to actually happen and occur. Like you and your friend need to go around campus enough times or move around enough times for you to actually meet each other. What the enzyme does is it lowers the activation energy, so lowers the requirement you need to actually meet each other. So it makes it a lot more likely to happen from reaction to product. Now, here are some summary of what does the enzyme do. It doesn't change the Gibbs free energy, right, from reactant to product. You and your friend is not gonna spontaneously meet someone else because of it, right? There's not going to be a change of the events happening. And enzyme also is not used up. Your classroom is not going to disappear on you once you meet your friend, right? It's also affected by temperature. So the hotter it is, perhaps the enzyme will be more active, or at a certain point it's going to just deactivate by itself and just doesn't work, right? If the classroom is too hot, it might just both avoid the classroom altogether. No shift in equilibrium. Yeah, so it's not going to affect whether the substrate is going to dissociate more or bind together more into products, or product splitting into more substrate, because it exists in equilibrium. Eventually, the substrates is going to turn into products, or products going to turn into substrate, and it's not going to mess up that balance of products to substrates. Sure, it can increase the efficiency, but doesn't move the overall tipping scale of the balance. And yeah, what it does is just lowers the energy required for that progress to happen. So, key thing, affects efficiency, not equilibrium. Now, what it does, right? No enzyme is a blue graph, and with the enzyme, lowers the energy. So you have your enzyme and your substrate on two separate entities, and it's going to have a certain chance and a certain rate of binding together, so K1, and a certain chance and rate of dissociating to K -1. This is just for reference, but for the enzyme substrate complex, it can also catalyze into forming the actual product itself. It's going to allow them to bind to each other into a catalytic process, to the enzyme as well as the end product. Remember, enzyme is not used up. We can visualize this also on what's called the Michaelis-Menten plot. So, as a starting point, you have a certain amount of substrate. Here is 0, right? When you have 0 substrate, of course, the enzyme is just not going to bind to it because there's nothing to bind. Now, as you throw in more substrate, then the reaction speed is going to rise because you just have more substrate to bind to, and you're just going to have more products being generated because more substrates, right? And you keep going until there's a maximum velocity of the reaction happening. Notice how the side graph here shows reaction speed or velocity. When you have products fitting in all the enzymes, and all the enzymes gets currently capacitated with the substrate, you just don't have more enzymes to work with, right? If you reach the maximum of enzymes you can use, all the classrooms are being used up. You just don't have enough space to progress it any further. That's why you reach a certain capacity of Vmax. At a certain key point we want to point out is Km. This Km denotes the substrate amount, the amount of substrate where it is half of maximum velocity. This is just a key point to remember. Km is at half of the Vmax, is the substrate complex, or the substrate amount when half of the Vmax is occurring. So you have your velocity equaling to the Vmax times the substrate amount, concentration, divided by Km plus S. Now what do we know? At very, very low concentrations, basically 0, S basically means 0, right? And Km is just an arbitrary number depending on that enzyme. So at very, very low in the beginning, V initial, S is 0, and then V overall just equals 0, right? That makes sense because 0 substrate equals 0 velocity. Yeah? And however, as you go up and up and up, let's say 1000 S, right, times Vmax is going to be divided by 1000 S over Km. At super high amount of substrates, S is going to be bigger Km, so you can ignore Km and just think of S as 1000. 1000 divided by 1000, that's roughly 1. So Vmax will equals to V velocity, and that makes sense because Vmax equals Vmax. The velocity has reached its maximum. Yeah? What we have here also is Vmax equals the K catalytic efficiency multiplied by the enzymes. When you multiply by the enzyme concentration, it's going to be showing how fast the ES, the enzyme substrate complex, converts to the products. That's just an arbitrary rate we have here. Now, when we substitute this into the reaction equation, we have Kcat times E and times S divided by Km plus S. Now, when we're at ES concentration, Km is much bigger than S, right? Because the S substrate concentration is not that big compared to what we have already in the Km. The velocity is just going to be equal to the catalytic conversion of Kcat divided by Km, which is our half Vmax concentration. Now there are common types of enzymes to go over. We have our ligase, isomerase, lyase, hydrolase, transferase, and oxidoreductase. Ligase, you can think of it as just glue, right? Ligament, like binding together. Isomerase converts isomers due to the isomer naming. Lyase, cleavage without using any tools, without using any H2O, all that, so it's just simple chop. Hydrolase does a cleavage like lyase, but using a water molecule. Transferase catalyzes a transfer from functional group, like maybe oxygen or hydroxide, to another group. For example, kinase transfers a phosphate molecule to another. It is a transferase. Now, oxidoreductase, think of the name oxido, so it does oxidation and reduction, and it transfers electrons. And that's for enzymes. And now we're going to move on to these part. So enzymes, they're nice when they're being used, but also we want to limit how often and where they get used. So we need an inhibition mechanism. Usually when you have an A product and turn to B product and turn to C product, if this keeps going, then you're gonna have so many C product when you don't even need it anymore. That's why we want the C product to halt this process of A to B, so keep the reservoir of A in check. We don't want to all use up right away. Think about your ice machine. When you press your cup against the ice machine, it's going to drop some ice, right? But when it fills all the way up to the tip, it's going to block the passage and going to prevent any from coming down, or you're going to use up all the ice. Yeah? So what this looks like in mechanism wise, you have your enzyme and you have two main sites. One is the active or substrate site, active substrate site where they bind to, as well as what's called the allosteric site. I know it's kind of hard to see, but it's allosteric. Let me rewrite it. You can see it better. Allosteric site. allosteric, allosteric site. Now, these two have special consequences when you're using them as binding. So we have different kind of inhibitors. We have inhibition by competitive, non-competitive, mixed, or uncompetitive. In competitive inhibition, this inhibitor physically blocks the active site and prevent the substrate from actually binding onto them. So what it does, it increases the Km. Remember, Km is the substrate concentration where half occurs at half Vmax, right? Because there's this inhibition on it, you need more substrate to reach that half Vmax velocity. So Km increases because you just need more substrate to overcome that inhibition. Vmax doesn't change because you still have the same amount of enzymes in general, and it's just going to go at the same rate on the top. In non-competitive inhibition, the inhibitor binds to the allosteric site. So that allows the Km to occur naturally because there's just the same amount of substrate coming along and they're just going to bind normally. However, it decreases the maximum velocity because some of the enzymes are made incapable, they're incapacitated. So you don't have as many enzymes functional as before, right? They no longer have a functional binding site for it to bind to. Like the enzyme no longer can bind into because the change in configuration from allosteric binding. Mixed, let's talk about uncompetitive first. The uncompetitive is special because it binds to the enzyme substrate complex. So it binds to the enzyme when it's already binded to the substrate and lock it in place. If it locks it in place, then the product is going to form a lot more easier, right? Because the Km, because they're already locked in place, so they can form a product. So that means Km is going to decrease because you need less substrate than you need to actually make that enzyme substrate complex and bind, right? They're already locked in that configuration, so they can form products easier. However, Vmax also decreases because you have less enzymes physically available to bind to new substrate, right? They're permanently locked like that, so you don't have any free enzymes. Now, mixed is just a mix between non-competitive and uncompetitive. They can behave either like non-competitive inhibitors or uncompetitive inhibitors, and depending on which, they can increase or decrease the Km. If it's binding to the enzyme by itself attached to the allosteric site, it's going to increase the Km, and if it binds to the enzyme substrate complex, it's going to decrease the Km. Now, this is a little bit tricky because you have to remember that no effect happens when a non-competitive but mixed, it does, because of the dual function it can do. The Lineweaver-Burke plot just allows us to visualize the Michaelis-Menten we had earlier, because it does a double inverse plot. So 1 over V over 1 over S. This means that we can identify easily what the Vmax is, because this crossing the border is 1 over Vmax of the y of the x-axis at 0 here, or the y-axis here, and the x-axis, like this line, you can see where it touches is -1 over km, and we can find out what km is from here. Last thing to note is cooperation. Cooperation happens when the binding of enzyme to a substrate allows or promotes the further binding of other enzymes and their substrates. So what that means is, think about you have a dance party. Everyone's just kind of standing along, not doing much, but suddenly the two popular kids started like dancing together, and everyone else want to follow example. They started dancing together too. That's what cooperation is. The binding of two together makes others kind of happy and want to like keep binding together too. Right? That shows a fast progression, like a sigmoidal graph. It goes up quickly. They want to bind quickly and they reach the maximum capacity real quick. So Hill's coefficient help us visualize this. If it's more than 1, then it's positive cooperation. If it's just at 1, then it's no cooperation. If it's less than 1, it's negative cooperation. So think about if you already have some people dancing, and then suddenly the not so popular kids start to like do all kind of messes around and do all kind of like wacky stuff, and makes people kind of annoyed and don't want to dance anymore. That's what uncooperative or non-cooperative binding does. Alright, and that's it for enzymes. Again, please let me know. I'm always fumbling a lot. This is in one take, first take as well. So yeah, this is Alan. Take care, and bye-bye.